Hello, everybody. Welcome back after lunch. I think we got a lot of ground to cover, so we're going to get started. I'm Catherine Havasi, and this is Rob Speer, and together we're going to tell you a little bit about how to take text and turn it into data that you can actually use. All right, so with the prevalence and prominence of natural language processing, it can be really tempting to try to add NLP to applications or other sorts of things that you're building. In fact, people have begun to expect that they can interact with a computer in a more natural way, whether it be through better user interfaces or whether it be through actual natural language. So there's a problem with that. To your computer, text still looks like this. And unless you're Icelandic, I bet you really can't make much sense of that. But you can still make more sense of it than you can if you're a computer. We can figure out a couple of things here. We can see that, for example, Margaret up there is probably a name. It appears twice. We can guess that this piece of text is possibly about Margaret. We can also guess that some of the short words that appear a lot are probably words like the and other sorts of common words that we call stop words in NLP. So there's a lot of issues that are holding computers back from actually understanding text. But luckily, there's a lot of different open source packages and different workarounds that you can use to be able to do something right now pretty easily with text. So when you start working with text, something that you're going to find out really quickly is that language is actually quite ambiguous. If you decide that that's a bug and you decide that that's something you need to engineer around or build a big complicated solution for, you're going to get stuck really quickly. The thing to do with ambiguity in language is to embrace it, because you really can't do anything about it. You're always going to run into text with multiple interpretations. Otherwise, no one would sell headlines, bad book headlines in Barnes & Noble. Everyone would play dodgeball, and Groucho Marx wouldn't have any jokes. And the world and the internet are becoming increasingly multilingual. And so you need to make solutions that generalize easily. You need to make solutions that generalize easily, or else you're going to get stuck as more and more people begin to use the web and begin to use applications in their native language. So usually when people talk about NLP, often they either gloss over things or they talk about really big ideas, and there are big problems with that and arguments about that. But we're going to focus on things computers can actually accomplish in a couple lines of code right now. So what would you actually want to do with NLP? So one thing you probably want to do, a very common thing that people want to do, is take out spam comments or trolls or other sorts of things out of email, out of forums, or out of comment posts. And so this is classification. This is also figuring out when people send you email, making sure that the email that is angry is the email you see first, or maybe the email that is awesome, depending on your preference, is the email you see first. And so to make sure it gets answered more frequently. The other thing you might want to do is figure out how documents are similar to each other. Is this news post something that is similar to the news posts you've read before? Does your organization tend to receive different types of messages? Is this particular message an outlier? That kind of thing. Another problem is obviously search. How can people find the information that they're looking for, even when it doesn't appear exactly like they typed it into the search box? So we're going to give you a whirlwind tour of common and useful data-driven ways to work with and represent text.
And so I'm going to start showing you some code examples real soon. So the code is all available at this GitHub repository. I'm going to leave that up for just a moment if you want to try and get that on your laptop now. It'll also be up again at the end of the talk. So I want to show you the simple things that you can accomplish right now. And the simplest thing we should start with, and these examples are all going to be in Python. There's all kinds of languages out there. They're all great. I'm using Python, especially because we've got this wonderful notebook, which will come up in just a moment, from which I can give you code examples right here. And let me increase the font size. OK. So first thing I'm going to do is make sure everything's Unicode, because there's pretty much no excuse for not handling text in Unicode these days. So if we want Python to split up words for us, what are we actually asking for? Words, you might say, are things separated by spaces. And if we ask Python to split up words on spaces and ask it what we get from that, then what we're going to get is, well, almost the words, but they have kind of the punctuation glued to them. Like this last word is actually spaces, period, quotation mark. So that wasn't quite what we were looking for. So what if we say words are sequences of letters that don't include punctuation? That's something that we can define with a regular expression. And so if we ask Python to find all those, we're doing better. And you just notice we got tripped up in one place, which is that the word don't turned into don followed by t. And so you can keep refining this. Okay, wasn't it naive to not include the apostrophe? Let's say that an apostrophe can be part of an English word. What do we get now? And yeah, now we missed another thing. And basically the point I'm trying to make here is that when there's a very basic thing to do in NLP, you might want to find somebody who's already done it because they might have thought of all of these things already. And there's this wonderful toolkit in Python called NLTK for the Natural Language Toolkit. And it contains a lot of the basic things that you need for NLP in a very understandable and even very teachable form. It's kind of a library that's designed for writing an O'Reilly book around. And there is one. So I can import NLTK, and let's ask NLTK to split this up. So we've got this text here. We're going to ask NLTK to split it into sentences with sent tokenize, and then ask it to split it into words with word tokenize. And what we get looks like this. And this is a kind of particular definition of words, which would more accurately just be called tokens, where in addition to words, we have the punctuation as separate items. And when there's a contraction, it gets split into two tokens. And this tends to be, this is kind of generally agreed on as the way you want to deal with English text. And there are some very English-specific assumptions in here. If you were working with text in a different language, you would probably want to start out with a different text representation. For example, if you're working with a language like Chinese or Japanese that doesn't even use spaces most of the time, you would probably want to use a different first step. Another thing you might want to see is, can we deal with suffixes? In English, you can have a root word that has different suffixes on it, and you often want to treat those as the same word. So here NLTK is going to help us again, and in particular, we're going to use NLTK's interface to a resource called WordNet. WordNet is useful for lots of things. It's kind of a computational dictionary, and one thing it can do is look up the root form of a word. So I'm going to say, okay, first split the text into tokens, and then, in addition to lowercasing the word, look it up in WordNet using the Morphe algorithm this is an algorithm for matching words with various endings. And if you can find it in WordNet, give us that, and if you can't, just give us back the original word. And this is the result we get. So now wondering has turned into wonder, and suffixes has turned into suffix. And this is a very useful thing, for example, when you're making a search index, among many other things. Okay, so once you've got that data, there are a few things you can do right away. One thing is you can represent your documents as just a set of word counts, and then you get this very familiar looking visualization of a word cloud. And on the one hand, this is a pretty cool layout. On the other hand, I feel like this kind of word cloud has kind of a wasted potential here, because the position of the words in the word cloud doesn't actually mean anything. The color doesn't mean anything. The orientation on the screen doesn't mean anything. There's a lot more data that we could be showing. If we had a better representation of what was going on with these words, we could make something that actually told you more about your text. And so one thing that I like to work on is taking this kind of visualization but making it better and more informative. When you have sequences of words, these are called n-grams, and we can look up statistics about those. This is a plot from Google Ngrams, which lets you look up sequences of words as they appear in Google Books, and it can plot them over time. So I plotted the terms computational linguistics, natural language processing, and text processing, and compared the frequency of how often those things occur over time. And we can see a kind of interesting trend here, which is that text processing was the first term to become popular in the mid-'80s, but then quickly declined as natural language processing picked up, because text processing just doesn't sound ambitious enough anymore. So very often, we're going to be representing documents as bags of words, that we just take the words in them and turn them into the number of times that word appears, and we don't even care about the order they appeared in anymore. So we've pretty much lost everything about grammar. On the other hand, if we had the grammar, it's not entirely clear we'd know what to do with it. So this is a very common representation. So if we take, we can look at a small part of a bag of words matrix. If we look at these 3 Shakespearean tragedies, we can compare the number of times that words such as woe and betray and revenge and death happen. And we'll come back to this representation, but keep in mind, we're not actually just comparing 5 words, that this is a table that would go on, it would probably be hundreds of thousands of words wide. And we'd probably want to also include some n-grams in it, not just single words. But that could make the table ridiculously huge. How do we decide which n-grams are interesting enough to represent? Like, if we have a text containing the phrase vice president, that's an interesting n-gram. It has a particular meaning. Whereas the vice is not such an interesting bigram. And of the is a particularly uninteresting bigram. How can we tell the system to make a word count for vice president and not make a word count for of the? And here there's a statistical test that we can apply. So we can make this contingency table where we find the probability that any particular 2 words are going to be the words vice president. Compare that to the probability of seeing vice followed by some word that is not president. Compare that to the probability of seeing not the word vice followed by the word president. And finally, the probability of seeing not the word vice and not the word president. And so this is something where you can apply a statistical measure to find out, is this cell occurring more often than you would expect given the other cells? And that is something, again, that NLTK can calculate for us. So that brings us to our second Python example. So I'm going to import some sample text from NLTK. And to show you what it looks like when we run bigrams on this sample text, here is the NLTK bigrams function on the beginning of Moby Dick. And so there are some kind of interesting bigrams here and some completely uninteresting bigrams here, such as dash dash having. But if we ask for the collocations, that is the statistically interesting bigrams, and NLTK will calculate those for us. And so here are the statistically interesting bigrams from Moby Dick. And this representation is a representation that's pretty dense in information, to the point where if I show you the top collocations for any text, you can probably guess what that text actually is. So here, this one's the Bible. Anyone recognize this one? So this is Jane Austen, and in particular its Sense and Sensibility. And this one, this one is Monty Python and the Holy Grail. All of these are sample texts built into NLTK. So now we've got this information. We can represent documents as these bags of words. What do we do with them? One thing we very often want to do is some form of classification. So there are lots of AI problems that basically fit into this structure. You have some kind of input, and there's labels that are the things that you want to describe about that input. From that input, you can extract various features and put those features into a machine learning algorithm so that it gives you a classifier. And then you can use that classifier to take new input that doesn't necessarily have labels and put the labels on it. And when you have this kind of process in NLP in particular, there are a couple things you'll see over and over again, which is that the feature extractor very likely has bag of words representations in it somewhere. In fact, it may be based entirely on bag of words representations. And the machine learning algorithm, well, there are lots of algorithms that you could apply. But one that you'll see particularly often in NLP is the naive Bayes algorithm, because it happens to work very well on data that is structured like language. So naive Bayes classification. So this is applying the idea of Bayesian probability, where you've got a class C that you want to predict given these features, A1 through AN. But you don't know those probabilities. What you know is the probability of seeing the features A1 through AN given the class C. But the Bayesian rule lets you reverse that. And then you just need to figure out how it applies when there are interactions between features. And the naive Bayes assumption is that there are no interactions between features. Every feature is completely statistically independent of all the others. And this is blatantly false, and it works pretty well. Naive Bayes made a triumphant burst onto the scene of natural language processing around 2002 when Paul Graham wrote an article called A Plan for Spam. proposing the first Bayesian spam filter. And when that was implemented, suddenly you didn't have to sort out your own spam email anymore. It was just remarkably effective. So, given that, let's make a naive Bayes classifier. So we're going to, once again, use NLTK, but we're also going to put it together with a Python module called scikit-learn, which is for making classifiers. So, we've got to import a bunch of things. In particular, we're importing a corpus of movie reviews from NLTK, and from scikit-learn, we're importing the things that we need to build a classifier. So let's get a list of documents, and these documents represent movie reviews, and let's take a look at one of them. So this is what it looks like in the movie review corpus. They've even tokenized it for us already. And so you get all the text, and at the end, you also get a label on it for whether it's positive or negative. And there's only 2,000 movie reviews here, but that makes it a great size to run right now in the middle of giving a talk. So we split it into our training data and our testing data. And now we're going to say, okay, let's make vectors out of all of the documents. These are basically bag of words vectors. And tell the vectorizer to basically take each document and make a vector out of its count and keep track of the targets, which are the target labels, positive versus negative. And so here we've initialized our classifier, and now we're going to tell it to train on the training vectors. It's done. It's really that fast. And so now, did it work? And the thing we asked to find out if it worked is how well does it do on the test vectors, which we didn't tell it about. And here we see the score. It got 80% of the movie reviews right, which is really not bad given 2,000 inputs. You might be able to apply another machine learning algorithm and improve that by 1 or 2%, but it'll also take many times longer. I really recommend using naive Bayes first because you get to iterate, you get to find out what the right features are and get feedback really quickly, and then you can try fancier algorithms. So, now what I want to do is find out what's actually going on here. I don't just want to see a number. Like, what is going on inside this model? So this is actually the most complicated code here because I need to peek into the internal state of this classifier. And I'm asking it, what are the features that make the largest difference in positive versus negative output? So I'm going to sort by those, and I'm going to show the most positive ones and the most negative ones. And so I've defined that function, and let's show most informative features. And this will tell us what makes a good movie review and what makes a bad movie review, based entirely on bag of words. So a bad movie review is one that contains words such as ludicrous, or unwatchable, or any mention of Steven Seagal. There's another one that I was curious about, which is 3000 that appears here. And you'll find many reviews saying, like, wow, this should be on Mystery Science Theater 3000, especially because these reviews are from the late 90s. And we can go down and see what are the positive things, like outstanding or lush or breathtaking. And so now we have a way of detecting positive reviews versus negative reviews. And it's kind of specialized for 90s movies, but we didn't have to give it very much input at all. And there are people who will, promote, they've got this state-of-the-art sentiment analysis engine, and it's probably doing, it's very often just doing this. So now you know how.
Well, that is the state of the art.
Yeah. So let's look at a different thing we want to find out about text. Instead of comparing documents to a linear scale, let's compare documents to each other. So let's bring back our bag of words representations of Shakespeare. And we want to answer something about how do these documents relate to each other. So one thing we can see here is that while there is no betrayal, or the word betray does not actually happen in Hamlet, but there is a whole lot of revenge compared to the other ones. You might say that Hamlet is more different from the other two than they are from each other. And more obviously, all three of these are much more similar to each other than they are to, say, Alice in Wonderland. Now, before we want to compute anything based on these numbers, we need to make sure to get these numbers into some kind of sensible units, because right now these are just the raw counts. And one thing going on here is that all the counts for Hamlet are going to be kind of higher because Hamlet is actually a longer play than the other ones. And The other thing you want to account for is that some words are really common and are going to show up thousands of times in any text. Some words are really rare. You want to correct for that. And that applies a process called TF-IDF normalization. So you want to deal with the fact that some documents are longer than others, and TF deals with that. That's term frequency. TF deals with that by saying, instead of having the count of a word, you start with the proportion of your document that the word represents. And then you also want to correct for the fact that some words appear more than others. And the way you do that is with IDF, which is the inverse document frequency, a number that goes down as a word appears in more documents. In particular, the IDF tells you how much information you get from the fact that a word appears in a document. A kind of funny thing you might have noticed here is that the death column went entirely to 0. And that's because every single book in NLTK's Project Gutenberg corpus contains the word death in it somewhere. So it decided that conveys no information. Death is completely ubiquitous in this corpus. If you want to find taxes, you'll mostly find that in the Bible, but death is everywhere. So as the words get more specific, then the number of bits of information you get from them goes up, and that contributes more to the TF-IDF. So now, when you've got the TF-IDF vector, so you've taken the bag of words vector and you've transformed it. So when you've got these TF-IDF vectors, these are things that you can compare to each other. They're huge multidimensional vectors, but the idea here is that if these represent geometrically vectors that have a small angle between them, then these are documents that are similar to each other. So the idea is that you would get the Shakespearean tragedies to be closer to each other than they are to Alice in Wonderland. To make this representation easier to work with, and also more powerful, in fact, something you want to do is called dimensionality reduction. So we've got these hundreds of thousands of features, and instead of working with each feature individually, we want to say, okay, computer, you can probably find 100 or so features that are combinations of these words. And how about you redescribe the documents in terms of these 100 or so features? That gives a simpler representation that takes up less memory. And also, because it's being forced to generalize, it actually tends to be less noisy in the end. So,
Also, typically you have way more words than you have samples.
yeah.
So you prevent overfitting.
Yes, that is another very good reason to apply dimensionality reduction, is that when you are training a machine learning algorithm and you have more features than you have documents, then your machine learning algorithm can learn pretty much whatever the heck it wants to. And if you give it a smaller number of features, then it has to start behaving. And the hope is that when you put your documents into this vector space, you're also getting something where terms are in a vector space, where terms that are similar to each other are things that have similarities in meaning. And this is an idea that we will come back to later. So here's a quick example of applying latent semantic inference, which is basically dimensionality reduction over text, using a Python module called gensim. So we're going to go back to the movie review corpus. And let's look at one particular movie review, and we're going to find documents that are similar to it. So this is a bad review of a movie called Virus. This is a disaster movie. It's got an alien invasion. A lot of it takes place on a ship. And we're going to find reviews that are similar to this one. So, because it's fun. Maybe you're looking for hilariously bad movies right now. Like Sharknado was really popular a moment ago for some reason. So we've made our bag of words out of every text we have here. So we've got a dictionary of 39,000 or so words over these 2,000 documents, and now we transform that with TF-IDF. And build a latent semantic inference model out of it, saying that we're going to turn these 39,000 words into 50 topics. And we just have to give this a moment to think. There we go. And so now we've got this model, what can we do with it? Well, we can use it to measure similarity between documents. So we make our similarity object, and what we're going to do here is query it for similarity to a particular document. So we want to again turn our input document into a bag of words and run that through the similarity object and see what we get out. And the rest of the code is once again going to be boring code for printing things out on the screen, including a brief summary of each document. And so let's look at what are the most similar documents. to that review we put in. The single most similar document is the review itself with 1.0 similarity. And then you get a bunch of other reviews. And a lot of these reviews are bad reviews of disaster movies, which very well may take place partially on a ship. And if we look at the reviews that come out, so we put in a review for Virus, and we end up getting a lot of reviews of Speed 2 Cruise Control and Deep Rising. And if you couldn't tell that these movies are all fundamentally similar to each other, you could also just look at the movie covers. So the question is this all there is to word meaning? Because we can ask this representation we built, what does the word alien mean? And mostly what it knows is that the word alien is something that appears near the number 3, and that it possibly has something to do with Sigourney Weaver. It doesn't know, for example, that an alien is a being from another planet. And that's because nobody stops in the middle of their review to explain that, because you already know it. And so this is kind of a problem with training a model on one set of documents, is that there may be this implicit knowledge that is not being represented there and will cause your model to actually fail when you give it documents that look even slightly different. And so what I'd like to have is a model of word meaning that represents things that are true in general, no matter what your set of documents is. One thing that can do that is WordNet. So here we come back to WordNet. And one thing WordNet can give you is this hierarchy of word meanings, that we have car and truck here, and these are similar meanings because they are both kinds of automotive, which itself is a kind of wheeled vehicle, and so on. And NLTK can give you access to this information in WordNet, this is pretty useful. I find this doesn't quite go far enough. I find this a bit rigid because you might want to know that a fork is an eating utensil, which is a kind of article, but you might also want to know that a fork is for eating. That fork and eat have this very strong connection, and that's one that you won't necessarily find in WordNet. And so I want to represent what are these things that people know in background knowledge, these inherent associations between words.
So think about it, what it takes to understand the meaning of a single sentence. If you see a sentence like, I bought food at the grocery store, there's a lot of things that you really need to understand to be able to understand that. You need to know that if you go to the grocery store, there's food there, you can buy it there. You typically don't eat the food in the grocery store, even though there's food in the grocery store, and that you take money and you exchange it for goods and services. These are all things that we take for granted when we interact with each other, but computers don't know these things. So how would we start being able to do this? We actually began a project many years ago, the late 90s, to start collecting information about how computers think about the world that people know as ConceptNet now, which is a large open source knowledge repository. And so we can take concepts we know about the world, like buy groceries and money, and connect them together with different kinds of relations. And we have about 17 million of these connections online. But to really know what those words mean, we really need to be able to add more words and more connections to be able to understand, the context of a given word or the context of a given fact. And if you take this out to its normal conclusion, you're going to end up with a whole lot of connections and a really big graph. And this is what ConceptNet is. And it has an online API that you can use. You can also download it yourself, but it's kind of big. And that's at conceptnet5.media.mit.edu, which will be up on the other things because there's no way anyone would have understood that. But compared to an expert-created resource like WordNet, this might seem like a big disorganized mess. But see, the point is, a big disorganized mess is exactly what dimensionality reduction needs to better understand language. So when we did this before, we used documents and terms, but now we're going to use terms versus terms to sort of understand the relationships between terms to each other. And so we end up building this space where different points in the space are different words and things are closer to each other when they're more related. So you can see different things in here are close because they're, more related.
And that brings me to the ConceptNet example. So this is the last code example. And I'm going to interact with the ConceptNet API here, except not really. I've already done all the interaction because I have no idea if I actually have an internet connection right now.
You probably don't.
Yeah. I'm going to import the Python modules I need, which is just requests, which is for interacting over HTTP, and JSON. This is a REST API, and there's absolutely nothing programming language specific about it. So the idea is that you can just get this data in your programming language of choice, in your environment of choice. So we've got this URL that you can send your queries to, ConceptNet blah, 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 /data/5.2. This is for version 5.2 of ConceptNet, which actually came out a couple days ago. And to get our information, we've got this function called ConceptNet lookup, where we just give it some URI that's defined by the ConceptNet API. And it looks something like this. So here C says that we're looking up a concept, /en means the concept is in English, because these concepts are going to be in a lot of different languages. And then you give it the root form of the word that you're looking for. And I want to say, okay, find the concept learn, and take all of the edges that are coming out of it. And show us, it's going to show us a sample of all of the edges that are coming out of it. There's actually more than this. Why did I do that? Yeah. Okay, so if I had remembered to just open up the output instead of hitting enter again, then it would be showing you things like, teaching causes learning, and learning is at location school, and things like that.
He doesn't have internet.
Yeah. And I remember not to do that for the remaining examples. And so, these are facts that can be useful on their own, and we can also interact with the dimensionality reduced version of these, where we just find out which things are most related to which other things. So here I'm going to query for the associations that tell us what are the things that are most related to the concept good and least related to the concept bad. And so here we get some things here. We get the concept good itself. We get some negation concepts here, saying things that are good are things that are not worse or not evil. And then you get things in a ton of different languages, including one of our data sources even included a text representation of American Sign Language, which is perhaps one of the less useful text representations you will come across, but it's in there. And so you've got all of these things in different languages, and that's, on one hand, that's really cool. On the other hand, you might want to filter it for just things that are in English so we get more things we can understand. So the next version I ask for is filter for things that are in English. And here are the things we find that are good. A lot of these are things that, from various sources of knowledge, people have indicated that they like being knowledgeable, feeling important, having good friends. People like to talk about themselves. And we can also see the opposite end of that scale. What are the worst things? Like being diseased, being in danger, losing friends, slow internet connection. And this is not just a linear scale. This is something you can query anything. So instead of looking for good versus bad, let's look for the things that are most related to travel. And you get things like jet lag and motion sickness, and journey and bike and read a map. And so these are all things that are represented because ConceptNet now has this very generalized understanding of what words mean. And it actually gains a lot from the fact that it's in different languages, because sometimes these connections between words are things that go across different languages. So I've shown you a couple of representations that are useful to use in representing text, but these don't inherently work with each other. So I showed you ways of doing supervised text classification, and then a different way of finding similarities between documents in an unsupervised way. And then instead of training on documents at all, I also showed you ways to find out in general the associations between words. It would be really nice if there was one model that could deal with all of these, so that, for example, you could start out knowing what words mean, but also add in domain-specific information so that you can find out what words mean in this particular set of documents. And that's something that Catherine and I started working on a while ago, and we started writing software for this, and that software turned into our company that's called Luminoso.
So currently people use our dashboard interface to be able to do things like figure out what color your various bottles of shampoo should be and what your things should taste like and stuff like that.
This is all based on survey responses,
yeah, things like that.
Just unstructured text that you get from whatever your data set is.
So, but what we really want to do is make a public version of this so that people can use it. And also because we took in all this data online, we figured out one of the best ways to actually train an AI system up is by having the AI system learn while you're doing something that you want to be doing already, regardless of whether or not it's make your application smarter or plain taboo. So we want to open this up to more people. So if any of you are interested in taking out a key, we'll be giving away a couple free keys. Well, we'll be giving away free keys to anybody who wants it here. So if you're all in the talk, you can come have one. In the meantime, or if you don't manage to get us, you can email that address and reach us, or just email us in general. And so that's it. Thank you, guys. This is a little bit of some of the stuff we work on. Here's where the code and the slides are, which will also be able to tell you where to find all these wonderful packages that you can use to do all kinds of things. In the meantime, we're happy to take questions about language and computers, or about any of this stuff. So thank you.